Hello everyone. Greetings of peace. This is parts 0 to 2 of Electric series. What is electricity? Electricity is an essential part of modern life and important to the world economy. People use electricity for lighting, heating and cooling, computers and electronics, machinery, and public transportation systems. On this video, we will tackle about the history of electricity. How does electricity work? And basic components of electricity circuits. So please pay attention and relax as we are now going forward. History of electricity. The first documentation in the history of electricity dates all the way back to 500 BC, when Thales of Miletus discovered static electricity by rubbing fur on amber. But it wasn't until 2,000 years later, in the 1600s, that English physician and physicist William Gilbert published the first theories about electricity in his book, De Magnete. The next major text about electricity, experiments, and notes about the mechanical origin or production of electricity was published in 1675 by English chemist and physicist Robert William Boyle. In 1752, Benjamin Franklin ran his famous kite experiment that sparked the discovery of electricity. As a prominent American scientist and one of America's founding fathers, Franklin tied a key to a kite string during a thunderstorm and proved that static electricity and lightning were one and the same thing. In 1831, the father of electricity, Michael Faraday, the English scientist, who is responsible for the discovery of electromagnetic induction, electrolysis, and diamagnetism, Michael Faraday discovered that an electric current could be produced by passing a magnet through a copper wire. Because of this principle, both the electric motor, where electricity is converted into motion, and the generator, where motion is converted into electricity, were born. In 1879, Thomas Alva Edison created the most practical incandescent light. However, he did not invent the first light bulb. Surprised? Although Thomas Alva Edison could be said to have created the first commercially practical incandescent light, he was neither the first nor the only person trying to invent an incandescent light bulb. In fact, some historians claim there were over 20 inventors of incandescent lamps prior to Edison's version. Even before Edison was born, scientists had experimented with making light bulbs. These bulbs burned out after a few minutes. Fast forward to September 1882, when a house in Appleton, Wisconsin became the first American home to be powered by hydroelectricity. The station that powered the home used the direct current, DC, system developed by Thomas Edison. Over the next several years, the direct current versus alternating current, AC, debate captured attention, as Thomas Edison and George Westinghouse, who championed AC, competed for contracts. In 1887, Nikola Tesla designed the alternating current, AC, electrical system, which would quickly become the preeminent power system of the 20th century, and has remained the worldwide standard ever since. Edison, who was revered as the leader of the technological revolution at the time, was set on a direct current, DC, system. He believed that this was the only way to go, and that alternating currents, the system that Tesla was pitching, would be too dangerous and uncontrollable. Tesla was positive that DC would never be efficient or strong enough, and his invention of the induction motor would help regulate and sustain the higher voltages. In 1895, Tesla designed what was among the first AC hydroelectric power plants in the United States, at Niagara Falls. Special mentions to the likes of George Ohm, Henry Cavendish, James Clerk Maxwell, and Alessandro Volta, as they have large contributions in electrical world. And they will be tackled on the next part. How does electricity work? Electricity works by getting a bunch of conductor elements together and creating a flow of electron-stealing patterns through them. This flow is called a current. Conductors need to be surrounded with insulators, so the electrons can only go in one direction. Once you can control the direction the electrons are going, you can use them to power or charge anything from a light bulb to your TV, to your electric car. All you have to do is continue supplying your conductor atoms with more electrons. The moment they run out of electrons to take from one another is the moment your electronic device stops working. This is essentially how electricity works. That is quite confusing, isn't it? Let us make it clearer for those who get confused. Every matter composed of atoms. An atom is the smallest unit of ordinary matter that forms a chemical element. Atoms are small particles, and put simply, they are the basic building blocks of everything around us, whether it is our chairs, desks, or even our own body. Atoms are made up of even smaller elements, called protons, positively charged, electrons, negatively charged, and neutrons, no charged. Protons are much heavier than electrons, but they both have the same amount of electric charge, except that protons are positive and electrons are negative. Because opposites attract, protons and electrons stick together. A few protons and electrons can form an atom. Atoms and molecules are still very tiny. They are too small to see. Any big object, like your finger, has more atoms and molecules in it than anyone can count. We can only estimate how many there are. Because negative electrons and positive protons stick together to make big objects, all big objects that we can see and feel are electrically neutral. Electrically is a word meaning describing electricity, and neutral is a word meaning balanced. That is why we do not feel objects pushing and pulling on us from a distance, as they would if everything was electrically charged. All big objects are electrically neutral because there is the same amount of positive and negative charge in the world. We could say that the world is exactly balanced, or neutral. Scientists still do not know why this is so. When electrical and magnetic forces move electrons from one atom to another, an electrical current is formed. Electricity is the presence and flow of electric charge. Its best known form is the flow of electrons through conductors such as copper wires. The word electricity is sometimes used to mean electrical energy. What is conductor? A conductor is an object or type of material that allows the flow of charge, electric current, in one or more directions. The behavior of an object that has been charged is dependent upon whether the object is made of a conductive or a non-conductive material. Conductors are materials that permit electrons to flow freely from particle to particle. An object made of a conducting material will permit charge to be transferred across the entire surface of the object. If charge is transferred to the object at a given location, that charge is quickly distributed across the entire surface of the object. The distribution of charge is the result of electron movement. Since conductors allow for electrons to be transported from particle to particle, a charged object will always distribute its charge until the overall repulsive forces between excess electrons is minimized. If a charged conductor is touched to another object, the conductor can even transfer its charge to that object. The transfer of charge between objects occurs more readily if the second object is made of a conducting material. Conductors allow for charge transfer through the free movement of electrons. Conduction materials include metals, electrolytes, superconductors, semiconductors, plasmas, and some non-metallic conductors such as graphite and conductive polymers. Copper has a high conductivity. Annealed copper is the international standard to which all other electrical conductors are compared. In contrast to conductors, insulators are materials that impede the free flow of electrons from atom to atom and molecule to molecule. If charge is transferred to an insulator at a given location, the excess charge will remain at the initial location of charging. The particles of the insulator do not permit the free flow of electrons. Subsequently, charge is seldom distributed evenly across the surface of an insulator. While insulators are not useful for transferring charge, they do serve a critical role in electrostatic experiments and demonstrations. Conductive objects are often mounted upon insulating objects. This arrangement of a conductor on top of an insulator prevents charge from being transferred from the conductive object to its surroundings. This arrangement also allows for a student or teacher to manipulate a conducting object without touching it. The best electrical conductor, under conditions of ordinary temperature and pressure, is the metallic element silver. Silver is not always an ideal choice as a material, however, because it is expensive and susceptible to tarnishing, and the oxide layer known as tarnish is not conductive. Similarly, rust, verdigris, and other oxide layers reduce conductivity even in the strongest conductors. The most effective electrical conductors are silver, gold, copper, aluminum, mercury, steel, iron, seawater, concrete. Other strong conductors include platinum, brass, bronze, graphite, dirty water, lemon juice. While electric charges do not flow freely through insulators. This is an ideal quality. In many cases, strong insulators are often used to coat or provide a barrier between conductors to keep electric currents under control. This can be seen in rubber-coated wires and cables. The most effective electrical insulators are rubber, glass, pure water, oil, air, diamond, dry wood, dry cotton, plastic, asphalt. Other strong insulators include fiberglass, dry paper, porcelain, ceramics, quartz. The shape and size of a material affect its conductivity. For example, a thick piece of matter will conduct better than a thin piece of the same size and length. If you have two pieces of a material of the same thickness, but one is shorter than the other, the shorter one will conduct better because the shorter piece has less resistance, in much the same way that it's easier to force water through a short pipe than a long one. Temperature also affects conductivity. As temperature increases, atoms and their electrons gain energy. Some insulators like glass are poor conductors when cool but good conductors when hot. Most metals are better conductors when cool and less efficient conductors when hot. Some good conductors become superconductors at extremely low temperatures. Sometimes conduction itself changes the temperature of a material. Electrons flow through conductors without damaging the atoms or causing wear. Moving electrons do experience resistance though. Because of this, the flow of electrical currents can heat conductive materials. Moving on. To generate electricity, you'll require a fuel source, such as coal, gas, hydropower, or wind. Regardless of the chosen fuel, most generators operate on the same proven principle: turn a turbine so that it spins magnets surrounded by copper wire to get the flow of electrons across atoms, which in turn generates electricity. Coal and gas work in similar ways. They are both burned to heat water, which creates steam and turns the turbine. Renewable energy sources such as hydropower and wind operate slightly differently, with either the water or the wind being used to turn the turbine and generate the electricity. Solar photovoltaic panels take a different approach. They generate electrical power by converting solar radiation into electricity using semiconductors. I think it becomes more confusing. Or is it not? Hold on, there is more. Have you ever heard of Ohm's law? Ohm's law states that the current through a conductor between 2 points is directly proportional to the voltage across the 2 points. Introducing the constant of proportionality, the resistance, one arrives at the usual mathematical equation that describes this relationship. Wait. I know you may think it becomes more complicated, but not. Just a brief history: in January 1781, before George Ohm's work, Henry Cavendish experimented with Leyden jars and glass tubes of varying diameter and length filled with salt solution. He measured the current by noting how strong a shock he felt as he completed the circuit with his body. Cavendish wrote that the velocity, current, varied directly as the degree of electrification, voltage. He did not communicate his results to other scientists at the time, and his results were unknown until Maxwell published them in 1879. Ohm did his work on resistance in the years 1825 and 1826, and published his results in 1827. Ohm's work long preceded Maxwell's equations and any understanding of frequency-dependent effects in AC circuits. Moreover, the equation states that current in amperes is equal to voltage in volts over resistance in ohms. Okay, just sit back and relax. Let us know the roles of these three, and how they co-related in electric flow, namely current, voltage, and resistance. I am pretty sure you are familiar with a water flow in the pipeline. This is known water analogy for electricity. Let's take the water tank as our electric source or battery, the pipeline as your cable or wire, and the faucet shall be our switch. The water flow is your electric current. The water pressure is the voltage, while the pipe friction and other obstacles that prevent proper flow is the resistance. Voltage is the electric pressure, or the electromotive force, that causes the electrons to move through a conductor, in this case the pipeline. Volt was named after Alessandro Volta, an Italian scientist who discovered that electrons flow when two different metals are connected by a wire and then dipped into a liquid that conduct or carry electrons. Let us go back to our topic. Just like in hydraulic system, the amount of water flowing is proportional with the pressure and inversely proportional with the friction. Similarly, in electric circuit, the current is proportional with the voltage and inversely proportional with circuit resistance. Thus we get this equation. Interesting, isn't it? How about power and energy? Most of the time it is frequently interchangeably used. Power is the rate at which energy is used or the rate at which work is done. In other words, power multiplying by time equals energy. Power is in terms of watts in electrical world, where power equals to voltage multiplied by current. So to put these two stated equations related to Ohm's law, we derive these various equations. So, let us give some example to use these equations. How about 110 volt against 220 volt? Which is better? Have you ever wondered why 110 volt is widely used globally? Yet turns out now that 110 volts in residential dwellings are slowly becoming obsolete. Why? Well, the US used 110V because that's what Thomas Edison chose as a practical matter when he was designing the first electrical lighting system. At higher voltages, the light bulb filament didn't last long enough to be practical. At lower voltages, it wasn't bright enough. So Edison chose 110V as his trade-off. Say that we have identical wires with resistance of 10 ohms each, while supplying either 110 volts and 220 volts. Using Ohm's law, we derive that 110 volt supply has 11 amperes, while 220 volts has doubled with 22 amperes. Thus, it means that when selecting the ampacity required, using 220 volts is capable of supplying current double than 110 volts. So in electric design, a smaller ampacity can be selected in selection of wires. As we can see, we can make the 220 volt system cables and wires smaller, thus more economical. It also has lower power loss and has smaller percentage of power drop. However, 110 volts is safer as it is less likely to electrocute you. Unable to complete our electric designs and ensure safety, we should learn how to arrange the circuit in various ways. However, there are two fundamental types of circuits. It is series and parallel circuits. A series of circuits refer to a circuit that has only one path through which current flow. In the series circuit, all the components are connected in such a way that if any fault happens in the circuit, the current will not flow through the circuit. The current in the series circuit is the same throughout the circuit. A circuit is said to be a series circuit when the flow of current is the same throughout all the components in the circuit. In series circuits, the current has only a single path. In a series circuit, the relationships between current and voltage are the exact inverse of those in the parallel circuit, where current is the same throughout while voltage and resistance adds up from one point to another. In a series circuit, all the components are arranged in a single line. If more than one resistor is connected in series, the voltage across each resistor is not the same, though the current flow is the same throughout the circuit. On the other hand, parallel circuits refer to a circuit with more than one path through which current flows. In the parallel circuit, all the components have various branches for current flow, thus, the current is not the same throughout the circuit. A parallel circuit refers to a circuit with two or more paths for the current to flow. In a parallel circuit, all the components have the same voltage. In a parallel circuit, the voltage across each element is the same and equal to the source voltage while the current is additive. In a parallel circuit, all the components are arranged parallel to each other. If the resistors are connected in parallel, the voltage across each of the resistors is the same. What are pros and cons of both types of circuits? For series. Pros. It has a simple design that is easy to understand. It does not overheat quickly. It has a higher output voltage so that we can add more power appliances. It carries the same current throughout the circuit. Cons. If the total number of components increases in the circuit resistance will be more. If a fault occurs at one point, the total circuit will break. Now consider this example: if one of the components has fault, all the series become incomplete loop and thus shuts down the whole circuit. For parallel circuit. Pros. In a parallel circuit, if any one component gets damaged, the current does not stop and continues to flow through the other components, hence other components work efficiently. In a parallel circuit, the voltage across every component is the same, therefore, all components work efficiently. In a parallel circuit, you can easily connect or disconnect a new component without affecting the working of another component. Cons. In a parallel circuit, we cannot apply an additional voltage source. A parallel circuit requires lots of wires for connection. What are the components for electric system? Like what we have discussed, enable the electric current to flow and move from one location to another, it needs a conductor. It can be either through wire or cable. What are the difference? The basic key difference between wires and cables is that a wire is a single conductor whereas a cable is a group of conductors. Although, these conductors are made up of a common material, copper or aluminum. Usually, the wires are bare and are twisted. But some of the wires are coated with thin PVC layer. And in case of cables, they run parallelly and are twisted or bonded together to form a single case. For the safety purpose, an inner and outer sheath is made. A wire is measured by diameter. According to the diameter of the wire, it will be measured by a gauge number. The smaller the gauge number, the thicker the wire. There are two types of electrical wires: solid and stranded wires. The two categories of single conductor wires are solid and stranded, also called braided. Solid wire is rigid and conducts electricity better. A solid wire has a single conductor and is either insulated or bare, and it is usually protected by a colored sheath. This wire offers a lower resistance and is best to use in higher frequencies. Using solid wire offers low cost. And the stranded wire shows high resistance to the metal. Stranded wire consists of smaller wires braided together. Stranded wires are less prone to breakage when flexed repeatedly, which is why this type of wire is common in phone chargers. A stranded wire contains many thin wire strands that are twisted together. These wires are used where the flexibility is required. Standard wire can be used over a long period of time. Comparatively, the standard wire has larger cross-sectional area than the solid wire. A cable contains a hot wire carrying the current, a neutral wire to complete the loop, and a grounding wire as well. A cable is classified by the total number of wires it is made up of and their gauge. These are the types of electrical cables. Twisted pair cable. A twisted pair cable includes two cables that are twisted together. This twisting can avoid the noise produced by magnetic coupling, and thus it is used to carry signals. Twisted pair cable is generally used in data communication and telecommunication. Multi-conductor cable. This cable has two or more than two conductors which are insulated, and their purpose is to protect the signal integrity. Both twisted pair cables and multi-conductor are known as balance line configuration cables. Coaxial cable. A coaxial cable has an inner conductor which is surrounded by a parallel outer foil conductor which is protected by insulating layers. In the cable, the two conductors are being separated from each other by an insulating dielectric. These cables are generally used in TV cable, as its performance is more stable than the twisted pair cable. Fiber optic cable. The fiber optic cable transmits the signals through a bunch of glass threads, and comparatively, it has a greater bandwidth than metal conductors, and that means they can carry more information and data. For this reason, fiber optic cables are used instead of traditional copper cables. Ribbon cable. It is a series of single conductor wires connected side by side to form a ribbon shape. It may also be called zip wire because the conductors can be separated from the ribbon. The wires are not encased together in one protective jacket, like the other types of cables, but rather individually insulated. NM cable. The most common type of home electrical wiring is the NM cable, also known as the Romex cable, after the most popular electrical wiring brand name. The NM cables contain 3 or more individual conductors, wrapped together in a sheathing, which is a flexible plastic jacket. Armored cable. When it comes to house electrical wiring, local ordinances are more strict than national codes. That is why you might find that in some areas NM cables are not permitted for use, and in these locations, armored or AC cables are used instead. In commercial buildings or residential constructions with more than 3 stories, AC cannot be used. THHN or THWN cable. 2 of the most common types of insulated wires are the THHN and the THWN. Unlike the NM cable, these are single conductors, each having its color-coded insulation. And they are protected by a plastic or tubular metal conduit. Without further ado, we will talk about wires and cable sizes. Generally, the size of a wire or cable is in AWG, American wire gauge. Although some use dimensions for wire and cable sizes as square millimeters, square inch, or circular mils. Wire and cable size selection are based on its amperage, that can provide electric load safely and economically at the same time. We will tackle wire and cabling size selections in the next parts. However, to ensure safer environment, the cable and wire shall be run through a raceway. Raceway is defined as a channel or wiring accessories so designed for holding wires, cables, or bus bars. Raceways are usually made up of metal, plastic, or any insulating mediums. There are different kinds of raceways, but the most common is what we call conduit. Conduit is a pipe used in all types of construction in electric systems. It can be metallic such as steel and aluminum pipe or non-metallic such as plastic. Conduit can also be flexible or non-rigid. The main purpose of conduits are to provide a means of pathway or runway of wires and cables from one point to another, to physically protect the wires, to protect the surround in case there is a fault in wiring, to protect the building and occupant. This table represents the maximum number of wires that can be installed inside a single conduit with respect to its size. Let's take an example. We have 3/8 AWG wire. What conduit pipe size diameter shall we select? From this table, we will select based on what our data will intersect. So we find in our example that conduit pipe 21 mm is enough for us to meet the requirements. Other kind of raceways can be cable trays and cable bus. Conduit support shall be considered stamped steel, malleable iron, C-clamp, hanger rod, pipe clamps, U-bolt, I-beam clamp and side beam clamp. How about outlet and receptacles? Is outlet and receptacles the same? The answer is no. An outlet is a point in wiring system at which current is taken to supply utilization equipment. It is any point that supplies an electric load on which consists of either metal or non-metal box into where the raceway or cable ends. To make it clearer, an outlet refers only to the box itself. It does not include the item inside. Take note, wall outlets are not wall plugs. Plugs are attachment caps coming from a wire such in appliances. On the other hand, receptacle are contact devices installed at the outlet for the connection of a single attachment plug. In mounting receptacles, for wall convenience receptacles generally it shall be 30 to 45 cm above finish floor line, while industrial areas shall be installed from 105 to 110 above finish floor line. Another notable components to consider are junction box and switches. Junction box is not an outlet and shall not be considered as an outlet. Junction box does not supply electric current to utilization device. It is an enclosure housing electrical connection, or a box containing a junction of electric wires or cables. Switch is a device that open or close the circuitry in an electric circuit. Once the terminal of switch gets in contact, the electric circuit is complete and becomes a loop, and on the contrary, when not in contact, the electric circuit is incomplete, thus does not supply any electric load. For safety measures in case of fault in circuit, we need a safety device to stop the loop instantly. This can be either fuse or circuit breaker. What is the difference between the two? By purpose, they generally have the same. But notably, fuse is cheaper yet replaceable once a fault occurs in circuit, while breaker trips whenever a fault occurs. Other basic electric components will be discussed in other parts in more details. So that's pretty it is. See you in the next episode of this electric system series. Do not forget to subscribe and like the video for more engineering stories. Again, greetings of peace.